So in this problem, we're given a rod with a length of L, a thickness of T, and inclined at an angle of theta from the horizontal, from the x-axis. And we want to find the product of inertia, that's Ixy, of this rod. Now, this rod actually, the way it's presented to us, because it's a very, very thin rod, the book tells us to assume that our thickness T is actually really, really, really small compared to L. Then we're gonna find it helpful to treat this rod in terms of its hypotenuse, if we were to look at it as a rectangular triangle, a right triangle. So first, let's explain what product of inertia means, right? So you may recall that moment of inertia for the x-axis was found by taking the integral of y squiggly squared dA. Moment of inertia for the y-axis was found by taking the integral of x squiggly squared dA. Now, product of inertia will be found by taking the integral of x squiggly, y squiggly dA. So that is product of inertia. So for a problem like this, you see that we not only need to find x squiggly, but we will also need to find y squiggly in order to solve this problem. So let's try to solve this problem. And the steps are pretty much similar, right? We set our differential element. However, we may be able to find some approximations that allow us to solve this problem a little bit easier than our usual step. So let's go ahead step by step and let's see what we can figure out, okay? So our first step is always to set a differential element. A differential element will be dA. And I can locate that differential element at some arbitrary point x, y. Now here, I'd like for you to look at the geometry of this shape. We could draw a horizontal or a vertical element. However, I don't think that will be very helpful for us this time. If you look at this rod, it seems like a pretty long rod, almost like if it could be treated as a one-dimensional element. So instead of trying to draw a horizontal or vertical element, I think it would be very helpful if we draw a differential element that is oriented along the direction of the rod. In other words, I'm going to draw a differential element that is oriented along the direction of the rod with a thickness of T, but then a tiny, tiny, tiny length of ds. So this length of the element, I'll just call it ds. And of course, the thickness of the element is simply T, which is the thickness of the rod. Now, my first question would be, can I do this? Am I allowed to do this? Remember, when we're trying to find moment of inertia, we should know that your differential dimension cannot be parallel to your axis. In the case of your product of inertia, right? Because we are dealing with both the x and the y axes, it'll be helpful if this differential element remains, right, at an orientation that is not parallel to either one of these. The rules are not as straightforward as with general moments of inertia, but at the very least, we know that we are not failing or we're not doing anything wrong by setting our differential element to go along the direction of the rod, which is not parallel to either of these axes. There are other simpler examples that we can look at, but let's focus on this one first, okay? So why do I think this is helpful? Because if I set that element in terms of ds, where s is simply a distance that I move, along this rod, then I can go to my second step and find x squiggly and y squiggly in terms of that distance. So for my second step, you know that I'm going to find x squiggly and y squiggly. And I'm going to try to express x squiggly and y squiggly in terms of a distance and an angle. So essentially, I'm going to try to use polar coordinates or something similar to polar coordinates. The only reason we're doing this is because our differential element, you can see here, is not oriented in the horizontal or vertical positions. So that's just a little bit easier for us to visualize it this way because we're treating it almost, right? Almost as if it were a one-dimensional element. So if we move along this line and we say that our movement along this line will be quantified by the variable s. So in other words, if s is simply an axis that follows this line, and theta is the inclination of s with respect to x, then what is x squiggly? I think this is better. This would make it visualize it better. What is x squiggly then?
Just s cosine theta?
That's correct. S cosine theta. And of course, we'll know that y squiggly will be s sine theta. Again, the reason we're doing this is because of the shape of the element, right? The element is oriented in such a shape that allows us to treat it as a one-dimensional element. For step number 3, we want to express dA in terms of our differential dimension. For step number 3, you may recall that we will express dA in terms of ds. So if you look at this element, and I'm going to have to blow it up here so we can see it a little bit bigger. This element that moves along the rod has a thickness of t and a differential length of ds. So what's the area of this element?
It would just be TDS.
TDS, that's correct. Can we integrate this? Does t change with respect to s? So as I move along my s axis, does t change?
No.
Okay, so it's a constant. So I can treat it as a constant and leave it as is. And of course, the fourth and final step is to integrate exclamation mark. The product of inertia is equal to the integral of x squiggly, y squiggly, dA. From step number 2, we get that x squiggly is s cosine theta. And we get that y squiggly is s sine theta. From step number 3, we get that dA is t ds, where t is a constant. And we need our limits of integration. Now here we are moving along the s distance, where s is our axis. So along the s distance, what are our limits of integration? If s is our axis, right, our distance from the origin moving along the direction of the rod, what are the limits? S goes from what value to what value?
It would just be 0 to L, right?
That's correct. Yeah, S goes from 0 to L. So if S goes from 0 to L, what do I have? I can take out my constants. Does theta change? No, right? So cosine theta is a constant. Sine theta is a constant. And t is a constant. So taking out my constants, I get the integral from 0 to L of s times s. So that's s squared ds. So if the integral goes from 0 to L of s squared ds, integrating this should be relatively easy. I have my constants, t cosine theta sine theta. And this integral is 1/3 s to the power of 3 evaluated from 0 to L. Evaluating this from 0 to L will give us, I'm going to write it down here, t L cubed cosine theta times sine theta divided by 3. And this is your answer. This is your product of inertia. If you feel that this looks a little bit disorganized, maybe a little bit clumped, perhaps you may benefit from the identity, right? You know that cosine theta sine theta is simply equal to 1/2 sine of 2 theta. This is just a general trigonometric identity. And I guess if you think this is just a little bit too disorganized, you can apply that trigonometric identity and get that this is simply equal to t L cubed sine of 2 theta divided by 2 times 3, which is 6. And that is the product of inertia for this element. At this point, are there any questions with this problem?
I'm just a little confused how we came up with 0 to L for our S length.
Yeah. So first off, because this element looks one-dimensional, I wanted to treat it as a one-dimensional element. So I said that my axis would be along the direction of the element, right?
Okay.
And I call this my S-axis, okay?
Okay.
So because we're integrating across ds, which means that we are integrating across this entire axis, we need to know what are the limits of S. And notice that at the origin, we're not moving along the direction, so S equals 0. And then we're going to move all the way to here, where S is simply equal to the length of the bar, which is just L.
Okay. It just threw me off because the S stopped at where that small dA is.
Yeah, I tried to make sure to keep this arrow just to represent that S is the direction.
Okay.
It's not from here to here, it's the direction.
Okay.
Yeah. We can also solve this with Cartesian coordinates. It's just going to be a really difficult integral to solve, as always. But yeah, back to Tyler's question, the product of inertia is the integral of x squared y squared to dA. So similar to moment of inertia, but we're dealing with both directions. Any other questions before we wrap up? All right. If there are no questions, then I'll see you in tonight's review session, and I'll see you next week for our final topic of the semester.